Hi everyone and welcome back. This is Luke from Catus Maths, and in today's video we're going to be looking at proofs, in particular the proof by contradiction. Here are some proofs that you may have read in your time studying maths. Proofs are fundamental for making theorems and propositions crystal clear that they are undeniably true based on certain facts. And in today's video we're going to be exploring why square root 2 is irrational. We will be using lots of visuals to help us explore this concept, as well as algebra. If you don't really know what a proof is, that's okay. This video will just go through it very informally. To see where irrational numbers were a real challenge for mathematicians, we need to go back about 2,500 years ago to ancient Greece, where maths played a fundamental role in not just learning, but astronomy, shape, art, philosophy, and even music. Mathematicians during this era of time primarily saw mathematics from the lens of geometry. Lines, curves, shapes, and planes were very important in describing the world around them. The very famous mathematician Pythagoras, or his school, the Pythagoreans, discovered this theorem of the sum of a right angled triangle being a squared plus b squared is equal to c squared. The ancient Greeks conceptualized this theorem geometrically through right angled triangles, and they measured that the lengths of the two sides of a right angled triangle, when squared and added together, should equal the length of the opposite or hypotenuse of the right angle. Let's see what it looks like with an example. If we draw a square that has a length of 3, and on top of that at the corner place another square with a length of 4, and another square with a length of 5 to create a right angled triangle inside these three squares. So that the formula a squared plus b squared is equal to c squared, we're now going to find the area of each square and add them together. The area of the two smaller squares is equal to the area of the larger square. 16 plus 9 is equal to 25. You may be wondering, are there any other side lengths that we could use instead of 3, 4, and 5? Yes, we can use many, and that's where we place the letters A, B, and C. Let's now replace these letters with 5, 12, and 13. Does the Pythagorean theorem still work with these numbers? If we do follow the formula, it should hold. 5 squared plus 12 squared equals 13 squared. Let's see if it's true. We get 25 plus 144 is equal to 169. So this holds. In fact, there are many numbers that could be used called Pythagorean triples. In fact, prior to the ancient Greeks, we have ancient Babylonia and even ancient Egypt being aware of the existence of so-called Pythagorean triples. We're now going to look at irrational numbers from a geometric perspective. Commensurable is a word to mean dividing two lengths by a unit equally. This will help us understand what an irrational number is geometrically. Let's take these two lengths, blue and green, and we're going to see if it divides equally with an orange unit of length. We see that the green length is equal to 3 orange ones. Let's see how many orange lengths can fit in the blue length. We see that's 3. We're going to add one more, so the blue length is equal to 4 orange. The ancient Greeks used this concept to identify which right-angled triangles followed the Pythagorean theorem. We could represent the blue and green lines as a ratio, 4 orange to 3 orange. We could use any number to describe commensurable ratios, such as 3 and 2. Rational numbers are any number that are commensurable. That is, they can be represented as a fraction, where the numbers p and q, and both p and q are integers, where q is not equal to 0. What about square root 2? Is square root 2 commensurable? Is it a rational number? Let's see how the ancient Greeks represented square root 2 as a right-angled triangle with lengths of 1. Here we have a right-angled triangle, 2 lengths of 1, and if we follow the Pythagorean theorem, c squared is equal to a squared plus b squared. Now let's take the length of square root 2 and 1, where square root 2 is the orange length, and the blue length is 1. Do you see how the unit square root 2 cannot be divided evenly and equally by the unit of 1 by the blue length? This means that square root 2 is incommensurable or irrational. Although we can see that the square root of 2 is incommensurable, it's not really enough to prove that it is irrational, although it's a good visual aid. We are now going to prove that the square root of 2 is in fact irrational algebraically. And we're going to avoid geometry, although there are geometric proofs out there. We're also going to rely on algebra and a proof called proof by contradiction. And this approach to proving a theorem or a proposition is to reverse the statement and to, for this case, say that, well, we're going to look at square root 2 and say that it is in fact a rational number, and we're going to use facts and definition and work logically using algebra until we get to a point in our steps where there is a contradiction, a falsehood that disclaims that square root 2 is rational. Our first definition for this proof will be an even number. An even number is a number in the form of 2 times k, where k is an integer. Some examples could be 2, 4, 6, 8, and it goes on and on forever. To make it clear, let's use some visuals. 2k, where k is equal to 1, so that number is 2. How about if k is equal to, say, 2? Well, we get 4. And finally, let's try k is equal to 3. We get 6. So I hope we all agree upon what an even number is. And with that, we are now ready to prove that square root 2 is in fact an irrational number. Let's begin our proof by contradiction by assuming that square root 2 is a rational number. That is, it can be represented in the form p divided by q, where q is not equal to 0, and p and q are integers that are not even or have no common factors, or they'll cancel out. We're now going to work through this algebraically. If we square both sides, we get 2 is equal to p divided by q all squared. And that is the same as 2 is equal to p squared divided by q squared. And now I'm going to multiply both sides by q squared, and we're left with something interesting. 2q squared is equal to p squared. We say that p is even because it is both divisible by 2 and a square of an even number is even. So we can substitute p with 2k, which we earlier defined as an even number. So let's do that. 2q squared is equal to 2k all squared. I've just substituted k for p. That is the same as 2q squared is equal to 4k squared. And if I divide both sides by 2 to get q squared by itself, we're left with q squared or p squared divided by 2. And if we simplify that fraction, we're left with 2p squared. But this is a contradiction, because both q and p can't be even, and as earlier stated, they would cancel out. So, it is true, square root 2 is an irrational number. I hope you enjoyed this video. Thank you for watching. All the best with your maths journey, and as always, I look forward to seeing you in the next one.